the system is acted upon by more than one forces, then in that case what to do? There's a force F1, this F2 at a constant angle theta, then F3, the weight of the block, there's a normal contact. Under action of all this force, the block will undergo displacement. So here it will acquire a velocity v. As usual, the forces. I want that expression for the velocity. So now work done. There are work done by the force F1, work done by the force F2, work done by the force F3, work done by the normal contact, work done by the weight. That should be equal to change in contingency. Work done by the force F1, how much? F1 bar dot S bar, F2 bar dot S bar, F3 bar dot S bar, N bar dot S bar, mg bar dot S bar equal to mv square by 2. F1 bar dot S bar. So what is the angle between F1 bar and S? It is 0. So we write only F1 is. Angle between this F2s cos theta 2. The angle between them 180, no? So also like a 180 minus theta 3. So look at this, also this angle between the displacement vector and F3 bar, 180 minus theta 3. So this will become everything F3 cos theta 3 into S. Why negative sign? Or simplest thing, F3 cos theta 3 will act opposite to displacement, no? Or angle between F3 bar and S bar, how much it is? 180 minus theta 3. So solving this, and this will be 0. Why 0? The angle between N bar and S. This is one method. So look at this. This is one way. So what we should do when many forces are acting, what we are going to do is like, we are going to calculate the work done by individual force, and we are going to take the algebraic sum of that. You see, algebraic sum. One will be positive, other will be negative. So what is the net work done when more than one forces are acting? What is the method? Find the work done by individual forces and take their algebraic sum. That should be equal to net work done. That should be equal to change in kinetic energy. So another student say that, can't I do like this? Means he says that, so can I think like this also? Can I means what is another way? That one, you'll calculate the net force acting on the system. Of course, work done by N and mg are 0, no? So can you go for net force acting on system? So what is the net force acting on the system? N and mg will balance each other. That will get eliminated. So sorry, that one. The net force, it will be along y-axis. You see the block will not move vertically up, no? We know. So therefore, F3 sine theta plus N plus F2 sine theta minus mg equals 0. So there's a one vector form. I am going for it. F3 sine theta 3, F2 sine theta 2 plus N minus mg equals 0. Then resultant forces along x-axis. And this is what the y component of force, no? I'll call this as y component. Then I'll calculate x component. What is the x component? F1, F2 cos theta minus F3 cos theta 3. So what is the F net is equal to Fx bar plus Fy bar. So I can also write net work done is equal to, and this should be equal to change in kinetic energy. What is F net bar? So substitute these values. write it, net work done. What is net work done equal to change in kinetic energy. So there are two approaches are there, no? What is the two approaches? Calculate the net force acting on the system dot product with the displacement vector. You get the net work done, and that is equal to again mv square. Or what you should do, you can also do that work done by individual force and calculate the algebraic sum. Okay, take the algebraic sum of work done by individual forces. So either of approach, which will be better. Suppose if you want to analyze clearly which force doing positive work, negative work, this is the thing. If you're just bothered with only answer, no, the second method. So from where this idea it is brought, I think you go for the dot product, no? If you go for dot product, what dot product says like a bar dot b bar plus c bar. Can we expand this? Can you remember this? So similarly, if there are can I also write like this? No problem. Both are same, no? Will agree all of you? Already we discussed in the vectors here. So from that particular property of dot product of vectors, I'm applying. So now let this be f1 bar plus f2 bar dot s. So what you can expand like this: f1 bar dot s bar, f2 bar dot s bar. So there are two ways are there, no? Calculate work done by individual force. Calculate work done by individual force. Take algebraic sum of that work done, not vector sum, because work done scalar. F1 bar dot s will get scalar. F2 bar dot s will be scalar. Then we'll get some quantity, and there is a net work done. Or what you can do, net force, you take the help of vector addition, calculate the net force acting on the system. Then you get the resultant force. Then what happens? Dot s bar. Both are same is telling that one. So this is equal to net work done. So in a numerical, what happens? It's left to you. If you directly want answer, you know you're not bothered about which force is doing work. Take the vector sum of all the forces acting, dot product of displacement. Or individually you want to verify which force is doing positive or negative work, no? Break up things and work out here. So the dot product is really is going to help us a lot, no? If more than one force acts on a system, yes, we do have two approaches. This is the from the idea of dot product. From there we have brought it. So today what you learned, like net work done by the force, more than forces, work energy theorem, all this basic idea. So let's introduce to the potential energy, that one. Next one more.